Hello, you beautiful people. So today it's the time for the solution of worksheet number 6, and there we had a look at the equilibrium reaction. So what was your worksheet? The worksheet was about a very simple equilibrium reaction. Just A is in equilibrium with B. And I gave you in the worksheet, I gave you the expression like this. The reaction rate can be expressed in terms of the conversion. So basically this is the reaction rate for the direct order, and this is for the reverse order. And I gave you two Arrhenius parameters, two sets of Arrhenius parameters, and yeah, some starting conditions. And what I wanted you to do is that you first calculate the equilibrium conversion XA star for a certain temperature range. And then we had to, or then you should change for different reaction rates and then find out what could be the best temperature path to get a certain conversion. Okay, then also given in the worksheet, if you have a starting concentration of 0B in the beginning, then your reaction rate simplifies to this equation, and then it's not very difficult. Then you just say, okay, in equilibrium your reaction rate must be 0, so this cancels out. So R is equal to 0, and then you can say, okay, you just put this on the other side, then you say, okay, your starting concentration is of no importance. And then you can just say your conversion in case of equilibrium is just K1 divided by the sum of the two rate constants. Okay, and how do you get the values for K1 and K2? Therefore you just use the Arrhenius parameters. So here you set in a temperature of example given 263.15 Kelvin, so this would be minus 10 degrees Celsius. Then you can calculate the two rate constants, and then you get your equilibrium conversion. Okay, so calculation of K1 and K2 with the Arrhenius equation, and then you can plot it with MATLAB, for example. And yeah, what I did here, I didn't choose minus 10 degrees, but I choose 100 degrees. So there you have a value that is better to see here in the diagram. So I calculated for a temperature of 100 degrees Celsius. I calculated the two rate constants, 4.8536 minutes to the power of minus 1, and K2 is 7.4341 minutes to the power of minus 1. And then just by calculating you get a value of a conversion of roughly 40%. And if you have a look here, temperature of 100 degrees, and then you go here, then you can see it's a conversion of 40%. So, and yeah, this is just plotted with MATLAB. So that was the easy part. As you can see here, this is an exothermic reaction. This means if you increase the temperature, then your equilibrium moves from the product to the educts. So this means your conversion is getting lower or is decreased if you increase the temperature. And if you would go to 300 or whatever degrees Celsius, then you would have like nearly no conversion at all. So you would end up here at 0 conversion for higher temperatures. Okay, second question. The reaction rate R shall now be set to fixed values. See table below. So I skipped the table here. But this means that R has a constant value. Let's start with, for example, 1 kilomole per cubic meters and minutes. For one calculation for this value of R, the according conversion XA for a temperature range of minus 10 degrees up to 110 degrees shall be determined. And so you have to decide about reality. You have to differentiate between reality and mathematics. So if you just do the mathematics, then you will also get negative conversions. So this doesn't make any sense. So you just have to ignore them. So in MATLAB you can just fit in the limits of the y-axis, and then everything is fine. Okay, and for this you should also plot the conversion to temperature curve. Okay, we start with the same expression for the reaction rate, but now we don't want to know the reaction rate, but we want to set the reaction rate to a fixed value, and we want to know what is the conversion depending on your temperature, and the temperature dependence here is inside the K1 and K2. So what do we have to do? You just have to solve the equation here for XA, so for the conversion, and then this is almost like before, but here you have the minus R inside the equation. So, and what you then have to do, so again, for a temperature of 100 degrees Celsius, you know K1 and K2, and you know the starting concentration, and if we start here with the reaction rate of 1 kilomole per cubic meter minute, then you also know the R value, and then you just type in, you have to use all the K values, and then you get your conversion for all temperatures. So again, if you type this in, then you will end up here with a conversion of roughly 31%. Okay, and this, if you want to do this by hand, this really will take a long time, so it's more useful to do it with MATLAB. That's why I put you my MATLAB code here. So I think you're a little bit advanced now in MATLAB, so it shouldn't be that difficult for you. So what I did is clear all first, then starting concentration, we need the universal gas constant, and then we need the Arrhenius parameters. So I just copied them from the worksheet, and then I said, okay, let's define a temperature vector. So from minus 10 degrees to 110 degrees. And for the Arrhenius equation, we need it in Kelvin. So I changed it just by adding 273.15. So let's choose purple. So T cell, for example, T cell would be a vector that reads minus 10, minus 9, minus 8, minus 7, and so on. And so for Kelvin, it's just then it's 263.15 and so on. And then you can calculate the K1 and K2, and this is also a vector with the rate constant. So, for example, this K1 would be a vector. Here you have K1 from temperature 1, then you have K1 from temperature 2, then you have K1 of temperature 3, and so on. So inside this K1 you have all the rate constants for your different temperatures. So starting from minus 10 degrees up to 110 degrees, and the same for K2. So this is a vector. This is not just one value, because we defined this T cell and T cal, we defined this as a vector. Okay, and then the code continues. Then you say, okay, I also want to have different rate constants. These are the rate constant given in your table. You start with 0.001 and you end with the reaction rate of 3. Then you say figure 1, clear all, hold on, box on, grid on, everything that you need to know to get nice plots. And then here you have a for loop. So I said, okay, I want to have it for all the reaction rates that I have here in this vector. I want to have a single plot. So here is the plot command. And then you just say, okay, my conversion is just what we had here in this expression. I just typed in here in the MATLAB code. So this is your reaction rate. So if you start with your reaction rate 1, this would be the smallest one. And then you have here K1. And again, since this is a vector, your conversion is also immediately a vector. And since you are doing vector manipulation, you have to type in here this this dot in front of your divided by sign. Okay, and this is how you get a vector for your conversion depending on your reaction rate. Okay, and then I plot it. So I want to have it on the x-axis. I want to have the Celsius scale for the temperature. I want to have the conversion on my y scale, and then you say display name, and here I do something to get a smart legend text. So I want to have the legend, I want it to have the values R, and then I want to have automatically the value of the reaction rate. So, and with this num to string, you can convert a number to a string, and then you can just put it as a text for the legend. So you could also just write here the value, but if you change it, if you, I don't know, change the value here or add a value here or whatsoever, then you have to change it here. And if you do it like this, then it's done automatically. Okay, and then I'm doing something I will show you on the next page. I want to know the maximum value for any reaction rate of my conversion. So, for example, if I have a reaction rate of 0.01, I want to know on which position is the maximum conversion. And this maximum function, this gives you the maximum value of your conversion, but also the position inside of your vector. So for example, here you could have the maximum conversion could be like 79% or whatsoever, and it could be the position in the vector could be position like 15. So this means if you have a vector with a size of 120 20 positions in it, then this means, okay, position 15 has the maximum value. And with this you can say, okay, I'm not only interested in the maximum value of my conversion, but I'm also interested in the according temperature. Then you just say, okay, I take the same position as for the maximum value of my conversion, and then I have the maximum temperature, or the temperature where the conversion is has its maximum. Okay, hope you understand it. Otherwise, just download the MATLAB code and play around with it. Then you should understand how it works. Okay, and then afterwards I'm plotting equilibrium, and here in this loop I created a new vector. So I'm saying, I created two new vectors. I'm saying, okay, my maximum conversion and my maximum temperature corresponding to this maximum conversion, and this I'm plotting here. Also, I called it locus of maximum rates. Okay, and then I'm adding the limits for the y scale and the x scale. So here you would also have negative values, and I'm just skipping it by saying my conversion must be below 0, must be between 0 and 1. Then labeling and legend, and basically that's it. And what you get is a plot that looks like this. So here's the temperature, here's the conversion, the red dotted line is equilibrium, and then you see here the blue line. This is the first one that we plotted. This is the maximum reaction rate. So I wrote here mole per liters minutes, and this is basically the same as kilomole per cubic meter minutes. So it's just other writing. Hope you won't get confused with it. Okay, and then you can see for a fixed reaction rate, my curve looks like this. So what does it mean? So if you are here, then you will see, okay, my rate constant is fixed on this curve here, and if you're approaching equilibrium, then, or if your temperature is further increasing, so if you're going here, this means that you are reaching equilibrium. Okay, and so here are different reaction rates, and they all look like this. And what I showed you here, the maximum conversion for a fixed rate, this one. So these are always the maximum points here on these lines. Okay. And I calculated here, where is it? There. I calculated one value for you. So it was for a temperature of 100 degrees C and a reaction rate of 1 kilomole per cubic meter. So how to find it in this graph? So we know it's 100 degrees Celsius and we need a reaction rate of 1 mole per liter minutes. So this is the whole curve here. And then you just have to find the intersection of this curve with the 100 degrees Celsius. And here you can see this is the value that we calculated, so 0.3136. This is the value that I showed you in my solution. Okay, so hopefully what I did here is correct. At least we checked one point and this makes sense. Okay, so let's now have a look at the optimal path and play a little bit around with this figure here. Okay, what was said? So your starting point should be a conversion of 0 and a temperature of 90 degrees. Okay, so what we could first try is, so here this is our starting point and this is the conversion that we want to reach. So we want to have, in the end, we want to have a conversion of 80%. And the first thing that we could try is isothermal operation. So we just go here until we reach a conversion of 80%. And what you can see here, that isothermal operation is not an option because this is above the equilibrium. So the equilibrium is what you can reach in a maximum case. And so if you keep the temperature constant at 90 degrees and if you have indefinitely time, then you would just end up with the equilibrium conversion of, let's say, 55%. So isothermal operation is not an option. This would not be a good idea. Okay, then let's say, okay, how about reaching the equilibrium? So let's say here we have our 80% conversion and then just go to this point to a temperature of, I don't know, 73 degrees or something like this. What about this point? So what if we want to achieve equilibrium conversion? So here's the problem. Our reaction rate here in this point is going to 0. And if your reaction rate is going to 0 and you want to achieve or you want to reach this point, this means your time or your residence time is going to infinity. So it's possible to reach this point, but it takes you, I don't know, hundreds of years. So also it's not very smart to size your reactor for equilibrium conversion. Okay. Then next idea. If we keep the temperature high, so 90 degrees is not an option or 73 degrees is not an option, so maybe we should cool it down and, for example, say, okay, I first cool it down to like 40 degrees and then go all the way up here and reach my conversion of 80%. So yes, this would work, but is it smart? No, it's not really smart. Why isn't it smart? If you look at your reaction rate, then you see, okay, here the blue line, there you have a reaction rate of 0.3, and here, so this the purple one is 0.03 mole per liter minutes. So if you choose this temperature path, then you are in a range of very low reaction rates. So your reaction rates are between 0.03 and 0.3 mole per liter minutes, and you are not using that you could have here something like a reaction rate of 1 mole per liter minutes or whatsoever. Okay, so this is not the best thing that you can do. Okay, and maybe it's better to think a little about our diagram. So let's say, okay, I want to have a conversion of what is it, like 63%. Then you can see, okay, the highest reaction rate that I can achieve for a conversion of 63% is a temperature of, let's say, 70 degrees Celsius. So you just go down and then you can see it here. So if you are moving in this direction, so if you want to have a conversion of 63% and a temperature of 60 degrees, then your reaction rate will go down. So the blue line is 0.3, the green line is 0.1. So if you move in this direction, then your reaction rate is getting lower. Why is it? So if you move in this direction, so here you have the effect that your temperature is decreasing, and this means with the Arrhenius approach that your rate constants are getting lower, and therefore you have a lower reaction rate. If you move in the other direction, if you say, okay, I want to increase my temperature, then you have higher rate constants. So K1 and K2 are becoming bigger, but you are closer yes, you are closer to your equilibrium, and this means if you are close to equilibrium, then your reaction rate goes down. Okay, so even if you go to this point here, you will find the same. So this means there's only one optimal temperature to any given conversion. Okay, if you say I want to have a conversion of 63%, then the highest reaction rate that you can have is 0.3 mole per liter minutes. If you want to have a conversion of what is it, 37 for 38%, then the best temperature for this is let's say 86 degrees Celsius or whatsoever. If you move in this direction, then your rate constants are getting lower. If you move in this direction, then you are closer to equilibrium, and this lowers your reaction rate. So this means I put the points here and the lines I put here on purpose. So this means the best you can do is to use this path here to get to your wanted conversion. So the best path would be, let's say 90 degrees Celsius would be our upper limit for the temperature. Then you would stay here. And then once you reached this curve here, then you try to change your temperature according to this curve, and then you would reach your maximum or your conversion of 80%. You would reach with the highest reaction rate possible. If you are here, or if you are even there, then your reaction rate would be much lower. If you are here, then your reaction rate would also be lower. So this is the best part that you can do. Okay, so this is the optimal path so this is the big problem, if the temperature can be controlled perfectly. So for this you would need a reactor where you can where you can use, where you can modify or influence your temperature very precisely to make sure that you walk along this path. This is not always the case, but at least we know now what the best way would be. And if you ask, okay, in what kind of reactor could you reach something like this? Okay, this would be something like a plug flow reactor. So if you remember this, in a normal plug flow reactor, you start with a conversion of 0, and then on the way through the plug flow reactor, your conversion is increasing. And then you can, so along the way of your plug flow reactor, you can change the temperature like this. The other option would be a batch reactor. In the batch reactor, you also would start with a conversion of 0, and then after a certain time, you could reach, after a certain time, and if you control the temperature properly, you would reach your wanted conversion. For the continuously stirred tank reactor, so such a temperature path is not possible because you only have one conversion that is valid for the whole reactor. So this is possible for batch reactor, for plug flow reactor, for continuously stirred tank reactor it's not possible. And maybe you can think about it for next time. This is like a oral homework. What would be the case for a recycle reactor? So maybe think about it. What would happen in a recycle reactor? How would this look like here? Okay. And then basically that's it for worksheet number 6. And I was asked for a new picture. So maybe you enjoy coloring this nice little picture. All the best.